Okay, so let's now look at the limit law here, and this is where we are about to begin looking at how to calculate limits without doing the tables. Because see, you don't want to always crank through the tables, right? The left-hand side table and the right-hand side table, it's going to take a lot. See what I'm saying? That's what we want to actually come up with some solid steps and better work with that, right? More effective solution right there, other than the table values. So, ladies and gentlemen, the two special limit laws, the two special limits that I put on the board right there, they also being part of the limit laws here. So law number one that we've had, right, is anytime you take the limit of a constant term here, of a constant, okay? So that's just a reminder, and regardless of whatever limit point it is, right? The limit comes out just simply the constant. Sounds good? So, really now the demonstration, the explanation for that is, see, I explained about this kind of function in our earlier learning, right? In our earlier days. Okay? So that function, when you're looking at the graph, see, depending on how high C is positively or how low C is negatively, it's a flat line. It's a constant function. That's why the limit point is on the x-axis. You choose wherever the limit point is, but your function remains the same height. See what I'm saying now? And that's why we have the special limits, but now we also consider that as among the limit laws here, one of the laws, taking limits, regardless of any limit point there, taking limits of the constant term, we always come out that constant. Sounds good with that? Okay. And then we talked about earlier, and that it's still among the special limits that we've just discovered, your simplest function on Earth, right? That's function x right here. And now we're letting x to get close to any limit point. Okay? It comes out a. It comes out just exactly equal to that limit point right there. Sounds good? So the explanation for that, I've given that before, and I can remind it again. The function x is simply just this. Nice, a 45-degree line, right? So you pick an x value, pick a value on the x-axis right here, we call that as the limit point right there. So as we keep getting close, see, somewhere far away it's this height, somewhere to the right-hand side it's this height, but when we get closer, right, it keep coming to that particular height at A right here. Okay? You see, my solid line here is intended to be real close to that dotted line right there. And then that solid line produces a height real close to this dotted line horizontally. See what I'm saying there? Okay? Of course, I'm a human being, so my drawing is a lot of time going loose on the scale like that. But so that's now we consider that special limits earlier as part of the limit laws. Sounds good? All right, so, but now among the limit laws right here, there's the next one right here. So now, a lot of times, and you've learned from your pre-calculus days that anytime you can just simply take any two functions, add them together, and then we consequently come up with another function, right? So the overall f plus g right here is a function. You've learned this since pre-calculus 1, right? So think about it, yes? The idea now is that as a whole function, there are two terms connected by addition. And so taking the limits, okay, taking the limits for x getting close to A right here. By doing so, taking the limits of a sum right here, that is the same as you are allowed it, right? It's a proven factor here. You are allowed it to find each individual limit. Limit of f, limit of g. Right? If you can successfully find these two limits, as x get close to the same limit point right here, and then the two results here, we add them together, right? That will come out with equal to the limits that we originally intended limit on that sum. Am I making sense so far? Okay. So this rule right here works similarly when we're in that case where you have the two functions connected by the subtraction. Okay? You can also produce another function that comes out as a difference of two functions. And taking the limit. Okay. Yes, this rule says you can simply take one separate limit for f, okay, one separate limit for g, right, and then subtract the two results. But when it comes to subtraction, the order of that subtraction, make sure you stay in that original order of subtraction. limit law number 3, limit law number 4 right here. Okay. People famously give it a name. I mean, you may see that throughout a lot of textbooks. I tend to stay away from names because name, I mean, knowing what you do is better rather than just mentioning names. But this limit law right here, it's limit of a sum. Right? That's how we call that particular law number 3 right there. And then here we've learned about how we can calculate. This law allows you to calculate the limits of a difference. So similar name right there. It's limits, okay, of a difference. Right. And so now on my board here, I'm short of space, will allow me to revise my, because usually, and you may even see textbook that combine, the law number 3 and 4 right here into just one universal law right here. That they call it like this. You just you put plus or minus. So either the point is either the two functions are either added or subtracted from each other, right? Taking the limits, it's just simply the same as finding the two individual limits, okay? And then either add or subtract them, the two results. And then so that right there, yes, in a more revised way we call that, it's the limit of a sum, right, or a difference. Right? Yes, you can call it number 3 or 4. 3 or 4. These two laws right there that we have. That's good. And then, so aside from those, now number 5 here on the list, among the laws here. Yes, multiplying any two functions f and g, you will come up to another function here. So this big function I'm talking about is a product, right, of some two other f and g functions. And yes, anytime you have a function, you will eventually be asked to find limits as x gets close to some value. See what I'm saying now? And so this law right here allows you to do the following. Anytime you're taking limits on a product, you are allowed to find the two separate limits. One for f, okay, one for g. Okay, find the two separate limits. Okay. Then whatever they turn out, we can multiply the two separate limit answers. And then that's the answer to the limits of this original product. And so this law right here, we refer to that as limits of a product. Cover limit of the sum, the limit of the difference. Now we're looking at the limit of the product. Right? Then number 6 right here, see, if you have an adding, then you can have a subtraction, right? You can have an addition and you can have a subtraction. So think about it. If you have a law for a product, you have to have a law eventually for a quotient, right? A division problem here. So number 6 right here, yes? Dividing any two functions, right? F over g or g over f, right? So the order of the division does matter right here. So keep an eye on how it's ordered. So in my demonstration right here, I'm putting f on the numerator, but the idea here is that we're taking the limits of a quotient. As x getting close to a limit point A. And so the law I'm about to write down here allows you to find the limits separately on f of x, right? And then the limits for g. Okay, find the two separate limits right here and then divide them out. Right? Yes, we refer to this as the limit of a quotient. Right? Leave me some space in this line number 6 here because I'm going to come back and I'm going to add in some extra details to that. Because line is not that simple. I mean, it's just the problem with human math on Earth right here. Anytime we have a denominator, I'll mention it. So think about it this way. It's still a little too advanced with these kind of things right here, but you see, if you're taking the limits, technically, if we're looking at that limit laws number 6 right there earlier, Let's say x go to 0 of an x squared, x squared minus 1 over x, for example. You see, a function like this, it's a quotient, right? It got some f right here, this is f, some g right here. So it's obviously, right now we're taking limits of a quotient. So it seems like, can we really do separate limits for x squared minus 1 and then a separate limit for x? The law says so, but here's the problem. If we're doing that, then the limit in the denominator here goes to what? To a 0, right? So can we really, whatever the outcome here that will turn out, can we really divide that limit on top right here by a 0? We really can't, right? And so we have to go back and revise that law number 6 that we have just stated here. This law is indeed sadly limited to those that, see, only when the limit in the denominator turns out non-zero. You only can apply this limit law right here when you know for sure that the limit in the bottom function is a non-zero quantity. Okay? Otherwise, things are not going to work. See what I mean? Right? Number 7 here, you can have, see, your function f of x can be raised to a power n, right? And then that becomes a new function right there. We can take the limit as x goes to a as well. Right? So this limit laws, I'm writing in number 7 right here, saying that anytime you're taking limit of a power, right? Limit of a power like that, you are allowed it. It's proven that you can just simply find the limit of the function before taking the power, find a separate individual limit for whatever that comes out, and then you raise to the n power. Okay. So yes, people refer to this as the limit of a power. So basically, these limit laws are here introduces the order of the work there, so that what can be done fast, right? And then what's after it and all that. Limit by itself is an operation as well. Like so, before calculus, you've learned, hey, addition, subtraction, division, multiplication. Those are all operations between numbers and things like that, right? But so now, when you get to calculus, limit is another operation additionally from those we've learned previously from the earlier courses, right? So that's why you've been knowing about the pandas, right? Order of operation. And so with limits right here, the limit laws try to allow that, try to introduce for us. When we introduce that extra operation right here, then how we are allowed to carry, you know, the whose see power is part of the traditional operation we've been knowing, right? But now with limits right here, limit of a power, meaning think about it. Here the order says you take the power of that function f first, and then whatever that is. Right? The next step, we take the limit. Right? But then the law here allows me, hey, we can reverse the order, take the limits, and then raise the power. That's why it's sort of like these limit laws are here. Another way of seeing that, it allows you to carry out a certain order of operation and how we can twist it around. Right? But so that's just too much talking about the theoretical side of it. Let's get to see how good it can be for us. Right? So limit laws is intended to be a one separate chapter or one separate big topic on its own. So let me restart the example number. Okay, let's look at example 1. Okay, so now we want to really evaluate. We will no longer estimate. The idea now is that we don't want to use table values. Okay, we don't want to just estimate, get a table on the left-hand side, get a table on the right-hand side, and crank through. That's too much. Let's say the limit here is x gets close to, anyone would like to pick for me a number? 3. Okay. X gets close to 3. Or the function here is 2x minus 3. Right? Alright, so here's how I'm seeing it. You see that this function, the entire 2x minus 3 right here is our function, right? Our main function. But let me now underline it. You can think about, this is 2x right here is some f of x. And my red notation here is just extra notation to explain for you. But when you're doing your real written stuff, you don't need to do all of these markings. You see what I'm saying now? But I'm underlining the 2x right here can be understood as one separate function f of x. the 3 right here can be regarded as another function, right? G of x. We can, and think about it, if g of x equals 3, it's a constant function. Am I being clear with that? Okay. Right? So knowing that, realizing the nature of there, here's how we move on. And by the way, there are 2 terms, right? F and G are connected by the subtraction. You see what I'm saying now? Okay. So this problem right here is we're taking limit of a difference. So now we have that large number 3 or 4, right? Limit of a difference. So the limit of difference allows me to find one separate limit on a 2x. So I'm talking about equals, right? To get to that answer right here, we can do one thing. Take the limits on the 2x function. See what I'm saying now? Okay. And then take away the limits for the constant term as x going to 3, x going to 3 over here. And then the next step I'm seeing, now let's hold on to this term right here, because really we have 2 separate limits to handle, right? But this word right here, let's leave it here for now. 2x, x getting close to 3. But do you recognize this limit? Is it among the limit large again? The function we have here is a constant function, right? So regardless of whatever it means, you could have suggested x going to 1 or x going to 0 for that, in place of that, number 3. But this 3 right here came as part of the function being a constant. See what I'm saying now? So that means this limit here is simply just 3, right? Limit large number 1 right there allowed us to make that conclusion. See what I'm saying now? Right? So the 2x right here, think about the 2x. The 2x right here is a product, right, between 2 and times x, right? 2 times x right here. So what do you see? It's a limits. The problem here, we tear it apart right here. 2 times x, taking the limits for 3 right here. That means it's equal to limit of 2, right? Times the limit of x right here. See what I'm saying? Okay. X getting close to 3. This is sort of like on a scratch work level. See what I'm saying? Okay. And so that's just a little bit of scratch work. So now back into the formal step right here. In the next step I can do, see, limit of 2. Right? X getting close to 3 times the limit of x. Okay. And minus 3 right here, because we've had that law earlier. So now once again, do you see the familiar laws have been among our work so far? Right? What do you see? What does that limit come out here? Just 2, right? See what I'm saying? It's a constant, right? This constant term, it's a different function. It's a different constant function, right? What about this? And now we're allowed to multiply a cos. I mean, so these are rule number 5 right here. I had on that board earlier. I mean, at least in this lecture over here, I'm talking about, see, the reason that we arrived from here to here, that was because there was the limit of a product, right? Equals to the product of the 2 separate limits problems. See what I'm saying? That's my argument for that, right? And so now what's the limit of this little part right here in my parentheses? It's going to go to 3, yes? So now it's 2 times 3. See what I'm saying now? Okay, 2 times 3, and then don't forget, subtract another 3, right? So now we have all of the solid value right here. We completely bypass table of values. What's your final calculation? It's going to be an overall 3, right? Does that make sense so far? Okay. The work we're doing there, I want to make you guys recognize another rule right here. So, and I'm really short at space, so allow me to erase this side. We need one more. You see, among the problem we've had, there was that term. See, there was like the 2x right here. The way how I'm seeing it, it's a coefficient. You guys familiar with that term again? It's a coefficient multiplied with some function, right? And so another rule we can recognize here is that we can call it rule number 8 again. So anytime you have your function comes with a coefficient, right? And then we take the limits, to a little point again. Okay? So when we're taking the limit of a function with a coefficient, then we can simply come with just simply find the limit of f of x itself right here. Okay? And then we, whatever that comes out as a result, we multiply with c. And the reason it's an easy law right here, easy to see, but I wanted to wait until this moment right here for you guys to see that and to put it on the board, because here's the thing. You guys can actually prove this on your own right here. See, think about it. The connection, what connects between the coefficient here and the function itself is the multiplication, right? It's a multiplication. See what I'm saying now? And so we've learned that rule number 6 or 5 earlier about so seeing that as a multiplication. Now we have a product between a constant, right? A coefficient is basically just a constant value multiplied with another function. See what I'm saying now? And so now taking the limit of this product right here is the same as, so before we come to that result, the rule number 5 earlier on my list, right, allows me to take one separate limit on the constant here, right? And then whatever that comes out, we multiply with the limit on the f of x. You guys following? Right? And so what does that come out right here for us? It seems like, yes, taking the limit on a constant function, it's just simply the constant itself, right? And we multiply with limit for whatever that will come out, right? That will come out for the f of x. And that's how we arrive at this quick little rule right here. See what I'm saying now? Okay. And so now think about it. Right now, just now, in this problem, I went this longer route right here because at this moment we didn't learn about that. That's a coefficient rule right there. But so think about in the future. Okay, I'm talking about for the any time later on. You can handle the problem like this. Like say right at this step right here. Actually right at that step. Right at this step. I would call this a sort of like the better solutions. Better solution. This longer way was just for me to explain the law like that, right? Those basic laws like that. But the better solution is now when you arrive right there, right? And you saw my arrow to indicate here. All you can do is just simply utilize that coefficient rule that we've learned, like the limit of a coefficient. So you can just simply put the 2 in front of your limit of the x. See what I'm saying? Now, so now because there's now legally a law that allows us to do this. You just simply apply the limits to that function, x, right? And then multiply it to the coefficient. See what I'm saying? And then minus the 3 from the previous step that we already found, right? And then the answer would comes out, see, 2 times, and we know this from law number 2, right? That has to, by the way, it should be the 3 here. Right? And that's going to come out the 3, right? And then subtracting the other 3, we end up with the same exact answer. And that's what I'm talking about, the better solution, right? The more effective. Okay. Any questions for me so far? Now let's move the problem up on the ladder right here in terms of difficulty. Get things a little more complicated. So how about we want to evaluate the limits, right? And our function here comes out x squared minus 3x plus 7, right? X comes to 2 here. Ready for moving in? Okay, and this is where I'm going to apply. See, definitely we don't want to use table of values anymore. So you got to get me my word for now for clear. The assignment I'm about to post for this stuff right here. I don't expect you guys to write down the table of values anymore. See what I'm saying? Huh? But I want you to carry through the limit law steps. Okay, because that's the way. Otherwise, it's going to take forever. So, how many terms do you see in here? 3 times, right? See, your function overall, that's why I put it in parentheses. Your function is a combination of 3 terms. You got subtraction and you got addition, right? So, see, limit of a difference or a sum allows you to do the following. So, that limit will equal to the limit separately for the x squared. You see how I put the x squared in parentheses right there? Because now I see x squared as one function. You guys following? Okay. And we're going to subtract the limits of the other function being 3x. Why is it subtract here? Because it's the limit of a difference. Sounds good? Okay. And then plus the limit of 7. See, I see 7 as one function on its own right there, right? Being a constant function. Sounds good? Okay, so the limit of a sum or difference law, like that law we've learned, law 3, 4 that I combine together, right, allows us to arrive here. Sounds good? And of course, don't forget, get for yourself into good habit here. Indicate the limit point. X get close to 2. Sounds good? Right. And so now in the next step, the limit laws right here, do we have a law specifically for this? So that's going to be plus 7, right? So clear, right? Do we have a limit law for this? Now that limit law says, see, now I see that it's a 3 being the coefficient, right? Multiplied with some simple function x. So I'm looking at 3 times the limit for x. See, one more step. You guys have to see there's a whole intention why we have to write it down like this. Because there's a limit law that goes from limit of a coefficient, right? Means you can just simply find the limit on an individual function and multiply at the end, right? The coefficient to that. And then the minus sign here, the subtraction sign, still got carried down in the next step. Sounds good? Okay. And then so, right here, what do you recognize? Limit of a power, right? It could be a power 3 in some other problem. It could be a power 10 in some other problem. See what I'm saying? No, but limit of a power. So what's the limit law allowing us to do this now? The limit law that says you can take the limit individually for the function. Sounds good? Okay. And then you raise that to the power 2 with that. Okay. Order with the operation. Right? And so now, in the next step, do we have a law that specifically handles limit of this simple function on Earth? It's that law right there, right? Whatever I said on the board right there, right? So that's why now it comes out. That's why now it comes out. That first term before the square, it's just going to be a 2, right? But then we are allowed to square that 2 limit again, right? Minus 3 times of that limit's 2 again, plus 7. Sounds good? Okay. And so, yes, it comes out, and then you do your calculation for me, right? It's a 4 here minus 6 right here, making it minus 2, so 5, all final answer in the end. Okay? Keep checking my calculation right there. I make silly mistakes like those all the time. There were days, I agree, there were days back in your pre-calculus course, right? Your pre-calc 1 or stuff like that. You do have a function f of x equals the x squared minus 3x plus 7 is simply just a quadratic function, right? And there's nothing wrong with substituting in. So if you substitute x equals 2 into your function, you have the 2 squared minus 3 times 2 plus 7. See what I'm saying now? So think about the consequence. For this problem here, think about the consequence that you skip all of these steps. I've seen a lot of people doing that actually. I've seen a lot of people doing this. Limits of x squared minus 3x plus 7, right? And then there's just one line here equals and x 2, one line here. 2 squared minus 3 times 2 plus 7. I've seen a lot, trust me, eventually someone's going to get into that bad habit right there. What's the consequence? When you're running it like this, you're leaving your reader to understand that all you did was simply substituting in the limit point into the function. Is that the thing that been calling that is critically bad for a limit problem right there? Okay? So the only reason that you arrived here, yes, it seems like at some step we arrived there, right? It does look like, I admit, it does look like that we're substituting values in, but the whole reason we were allowed to get there because there were a whole bunch of limit law steps applied there. See what I'm saying now? So, sorry to say, but these steps here are quite critically required. See what I'm saying now? Okay. We call it part A for the example. Now part B of the example, let's look at a function like this. How about we have there's a 3x minus 2, so that's one function, but we multiply that with a square root expression, and then there's an x squared plus 1, okay? And then here we want to find the limits as we let x approaching 1, okay? Right, so now we call it part B of the example. It's just same ultimate understanding that we are trying to apply, all of the limit laws there, okay, into solving the problem. All right, so ready for getting in? So when you're looking at the order of operation, and aside from taking the limit right here, then we have a function here and it being in product, right, with that, whatever inside the square root right here. So the square root function right here, and in that 3x minus 2, there are two separate functions, so there's a product between them, right? So in that way, yes, the limit laws that we've learned about taking the limits of a product, right? So taking the limits of an overall product means we can take one separate limits for one separate limits for 3x minus 2, and we multiply with the same limits, but separately taking on the square root of x squared plus 1. You guys with me on this? The same limits to letting x get close to 1, but we apply it separately on the two functions, right, of that, on the two separate functions of that beginning product. Okay. So that limit laws that we've learned, you see on the board, I'm writing that as law number 5 right there, right? But at one day I want you guys to be independent with those. You don't tell me it's law number 5 or law number 7. Because last year, exactly the same time, I was calling that law number 3, for example, right? The point is it's the limits on a product. Right? Taking the limits of a product right here. So that's what we did. We tear it down to two separate limits on the two little parties of that. Now, in the next step, sooner or later, we have to deal with that square root, right? So now I want to add in, before I proceed on right here, let's get back to that page with all of the limit laws, and let me add in the one last, derivative version, deriving version of this. You see, similarly to the taking limits of a power right here, a lot of times you can have your function being put inside some root, some nth root. See what I'm saying now? Okay, and then we take the limits. So this law right here is sort of like taking the limits of a root function, right? Of a rooted function right there. And we can call it law number 9 in our list right here. But see, by doing that, now, don't you agree with me on this very narrow corner right here? F of x, but being inside of some nth root, it means the same as f of x, but raised to some power, right? But power 1 over n. You guys agree? So realizing being a root is exactly the same as a power. The way how it works will be very similar to the way how we take limits of a power on a function. So meaning ultimately this means that you can just simply take the limit of your function separately. Okay? And once we're done, right, we take the nth root on that result of the limit. See what I mean? Okay, so I was proving it by simply making the analogous argument with how we did that with powers. Okay. All right, so now applying that, just now, the next limit law that we've just learned, and so in this property here, now allow me to decide leaving this here for now. So I'm leaving the limits for the 3x minus 2, same here, right? X, 1. But then on the next one here, I'm going to multiply, see? So now I can, see this is a square root, right, of a function x squared plus 1 inside of that. So now that means I can just simply find the square root limit law I just now introduced. Say that I can take the limits for the x squared plus 1 by letting x get close to 1. And then whatever that limit comes out, I'm going to multiply, and I'm going to take the square root. So the square root of the limits here will multiply with the limit result from the 3x minus 2. Okay, so that's how I'm breaking it down into the little steps like that. Sort of like we're swapping the order of the limit operation like that, right? We're putting that in the different order like that so that we can eventually get to the actual work. All right, so now at this point, things are a lot laid out for us right here. The only challenge, the only thing that's new is introducing the square root right here, but once we pass that point, things should go a lot easier. So again, on this separate limit work right here that I underlined, right? And we're talking about, we want to find the limits of the 3x, one term, minus the limits of 2, right? Yes, x to 1, x getting close to 1. Limit laws allows us to do that calculation, right? That part comes out as 2 separate terms. And then the square root expression, okay? This inside part right here is the same as you're allowed to do 1 separate limit work on the x squared, right? And then 1 separate limit work on the constant term 1. You guys see how I'm breaking it down like that? Right? There's a way how we lay down these order of operations. And so in the next step, back to the first group right here, right? And I'm looking at that first term right here, taking the limit of 3x is the same as taking the limit of x by itself. But letting x get to 1, and then we can multiply that by 3. Right? And then we're subtracting the limit of 2, the constant term, and then eventually it's all going to break down. Right? And then in the next group right here, inside the square root, now I'm looking at, see, limits of these powers, right? So we can do taking the limit separately on the simple function x, and then we take the power 2 afterwards, right? We're allowed to do that. And then the last term right here, the limit of the constant term 1. Everything is done here inside a square root. So I'm swapping the order, and some steps I'm combining, multiple little steps together. Right? But make sure you show all of the limit laws are connecting from one to another. So now we have everything laid down right here. Limit laws, at least among the limit laws number 1 and 2, and those special ones that we've learned, right? Sort of like the foundation. This will go to 1, right? And so we got now 3 times that limit to 1, because that simple function, right? That simplest function x right here, when we let x approach to a limit point, that limit comes out to simply that's 1 right there, right? And then minus, now taking limits for any limit point here, taking limits for a constant function, it remains constant. That's why now we have 3 times 1 minus 2. So things starting to look like we're substituting values in, but they're not. Right there has been a whole sequence of steps right there that how we apply the limit laws to make it work. Right? And then we multiply by 2 by the square root. We're taking the square root up. See, so I'm taking, so this, once again, that part right here, from our previous understanding, it's going to come out in 1. So it's 1 square, 1 then square, then plus another 1 right there, right? And then after whatever that is, we can take the square root. And so now it's all completely numerical, right? And we can just go ahead and do the final evaluation of that. You guys would be on that? And so the final answer should be a square root of 2, right? If I'm calculating correctly. Yeah, so yes, you can rearrange your steps a little bit, and that's why it's still different between Mr. doing and how you do it, right? And that makes you, you know what I mean? Right? The idea, the only fundamental expectation I have is you make sure you guys show all of the laws and how you apply to get from one step to another step on each of the little elementary part of your the overall function. That's all it is expected. Okay. All right. And so the whole example 2 just shows how we are using all of those limit laws like that. But let me now tell you, these limit laws here, we call them, they are the basics, just the basic limit laws. Yes, we definitely bypass using table values, right? And we come to some solid work right here, and it doesn't take us much time because table values, sometimes you have to go with a real lengthy table value just to get some limits estimated, and it's not solid. See what I'm saying? No? But now I'm talking about we have a solid answer here because we apply these laws. Yeah. Okay, so from this point on, we no longer have to use the table of values. But now, the reason I'm calling these are only the basic limit laws because there's still limitation. For example, this rule here, we can only use this law right here only when the limit in the denominator is a non-zero limit, right? But sadly, a lot of time bad news comes around. Let me tell you this. So let's look at the next kind of problem here. We still want to evaluate the limits. But I decided to put that in a new example right here so that you can see, you can make some differentiation between the two. All right. Example 3, we still want to evaluate the limits. X squared minus 5x plus 6. X squared minus 2x minus 3, and we want to take the limit as x get close to 3. So with this problem, yes, you can call it part A. I do intend to give another one after this one. All right. So let's see what we can do by just within the limit laws here, the basic limit laws. So basic limit laws tells me, and how about for now, I suggest keeping that on scratch work, okay? So this starting limit right here, x squared minus 5x plus 6, right, over x squared minus 2x minus 3, right? Basic limit laws tells me that I can take one limit on top right here, right? It's a limit to whatever limit point it is. And I'm going a little quite, rushing here. do that, right, over one separate limits for the x squared minus 2x minus 3. See what I mean? Okay, that's the basic limit laws, right? And then the basic limit laws allows me to separate it out into separate terms. So we got the limits of the x squared minus the limits on the 5x, right? 5x and minus the limits of 6 right here. And then the same way that happens in the denominator, right? The limits for the 5x and minus the limits for 3. Okay. And then think about, I'm skipping, I'm hiding a few steps right here. But think about the far impact right here. Eventually, it's going to run into a what? Eventually, at some point, it's going to run into a 3 squared, right? Minus 5 times 3. See what I'm saying now? Okay? Minus a 6. 3 squared minus, I had a typo right here, it should have been a 2x here. Okay. 2x times 3 minus a 3. You guys following me on that? Okay? And then we come out with what kind of answer is that? What's that? Yeah, I mean, it comes out with a, for now, it's just divided by a 0 limit. Right? These are all 0 limits. See, we're not substituting 3 in there. We get an x close to 3. See what I'm saying now? But as we let an x get close to 3, the numerator gets to whatever, but the denominator goes right to 1. I mean, right to 0 right here. Which is where, this is where I want to point out that we fail using, I'm gonna have to say, using the basic limit laws, especially the law, taking the limit of a quotient right here, we fail big time right here, because we fail right into that, critical, the exception, right? That rule is, that limit law works anywhere except for when the limit goes to 0 in the denominator. See what I'm saying now? So that's where the problem starts right there. So now, the way we handle it. And sadly, a lot of time, you see the limit laws on the quotient right there, indicating that we cannot apply it when you have a 0 in the denominator, but it will keep happening like this. We will, if you use the basic limit laws, you will quickly find out that the limit in the denominator will go to a 0. So in that case, here's how we're handling it. We gotta use some algebra. Okay, so when basic limit laws fail here, we use some algebra. Now, I'm talking about before taking limit. That's why I'm leaving the limit sign hanging out right here. From your pre-calculus days, you've learned that we can factor out the x squared minus 5x plus 6 into an x minus 2 and x minus 3. You guys agree? Okay. The denominator here, you can also factor it out into an x minus 2 times, and actually I'm like, x minus 1, right, times x, actually it should be an x plus 1, right, times x minus 3. You guys agree with me again? Okay. We apply the factoring technique that we've learned in some algebra courses before our time here. Right. And so the major reason that I'm allowed to do all of these algebra things is because I'm only getting close to 3, but I will never substitute x equals 3 into the function. So that's why it's completely okay that we do all of the algebraic manipulation on our function, on our expression here. And so now what's the advantage? Now I can cancel away the x minus 3. See what I'm saying now? And then so the function here reduces down to, and still we haven't done any limits operation yet, so I'm leaving it hanging there. Right? We got x minus 2 over x plus 1. See what I mean? Because once again, keep in mind, we're not letting x equals 3. We're only letting x getting close to 3. That's what limit is all about. So now at this point here, you can quickly check that, hey, the denominator will no longer approaching 0, right? The denominator will approach 4 because it's 3, the plus 1 later on, right? At some point. See what I'm saying now? So now at this point right here, in my language, I keep sharing with many of my students, I call this the safe zone right here, because you land into a zone where you can safely, apply basic limit laws into this, right? So this point right here, I can call that it's a safe zone right here, where you can safely apply the basic limit laws. So be aware. My point of this example is that be aware that sometimes you have to do some algebraic, work around like that before you apply these basic limit laws. Okay. So now back to the problem right here, continuing with the basic limit laws here that we have. Now it shows, yes, there's a limit of x minus 2 on top, right? Over the limit of x plus 1 in the denominator. See, right now you guys are count one and you just began into this not too long ago. So I really want you guys to write down your steps. But see, for example, the count three people who work with me just now, I didn't even bother that they have to show all the steps because their work is to find the limits for a bigger problem, for a much bigger problem. So I don't want them to waste their time on just little steps like this. But for you guys in here, because I want to train your mind process for that, right? And then one day when you arrive there again, then you can let go of all of these little small processes. Okay. So now 2 separate limits. Then yes, limit for x, limit for 2, right? And limits for x, and limits for 1. See, I can bring up multiple laws in one step like that, right? So now it comes out clearly 3 minus 2, right? 3 plus 1. And the answer comes out simply just a 1/4. That's what I'm saying. So we have found an answer for that, right? So once again, we will be getting into those kind of problems where you must apply some algebra, right, before applying these basic limit logic. But once again, nowhere in these problems that we have to use table of values any longer because we want to completely depart away from table of values. And let me remind you, back in just earlier lecture when I was talking about table of values, I did bring in a problem like this, right? In x squared minus 4 and over x minus 2. Remember that problem again? And we use table of values to approach this. Okay, and then as x getting close to 2 here, for example, what was our limits? We came to 4, right? But we got this answer completely because we approximate with table of values. We estimated it, right, with table of values. You guys remember? Okay? But see, think about it this way. With whatever you have just learned right here as an extra problem for you. See, we're not substituting x equals 2 into this because that's going to fail big time, right? But how do we end up 4 aside from using the table? X squared minus 4 is factored into x minus 2 times x plus 2. You guys agree? Okay. And the x minus 2 in the denominator stays the same. But see that now as a factor, right? One separate factor over here, and then we haven't done any limit yet. So we're holding on to that limit right here. And as a matter of fact, with this problem right from the beginning, just simply applying the limit laws, you're going to have a 0 limit in the denominator, right? That's why we have to go through all of these things right here. So now I'm going to, with this function right here, see, canceling out the x minus 2, right? I'm looking at it, and I don't even need to draw the fraction bar here, but it now reduces down to just the limit of x plus 2 over here. When x comes to 2. You guys following that? Now, see, safe zone is here, right? Safe zone is here, and now we can just go ahead and do the usual limit work, limit for x plus a limit for 2 for this, right? And it comes out just 2 plus 2, right? Which is making it 4 altogether. So now we did that completely without a table of values. We don't need a left-hand side table. We no longer need a right-hand side table anymore. You got the idea? Right. But what we've done here is that we recognize that, hey, we can apply the basic limit laws, and even before basic limit laws apply, we gotta quickly know that, hey, it's gonna be a 0 limit in the denominator, right? So informal steps, we're here talking about informal steps. Maybe throw me a line throw me a line that, hey, this limit of the x squared minus 2x minus 3, I'm talking about this particular problem right here. This is the denominator. Throw me a line saying that this limit right here will equal to 0. And I'm not going to get too far into how you have to show that right? But you can just, you just write it down right here, and then from that point we kind of branch out and apply the algebra before the basic limit laws. Right? And that's the way how I carry out the steps, and we present all of the proper steps, right, to whoever reading our work right here. See what I mean? Right? So let's get you guys to another one. So keep in mind that now my intention for these problems now is we will have a lot of times the critical spots where we fail that rule, that law of taking the limits on a quotient right there, because we have a 0 limit in the denominator. So part B right here, how about I'm going to take limits. And seriously, I'm getting tired of using x as a variable all the time, so how about t over here as being our variable? T going to 0, I got t squared plus 9, okay, inside of the square root, and then minus 3, and then I'm dividing that by t squared again. All right. All right, ready for action? See, once again, for a proper indication, immediately the limits as t gets to 0 for the denominator t squared here, that goes to a 0, right? You guys agree? Right out from the box right here. In its most natural setup right there, right? The limits of the denominator, right, show the 0. That's why we just can't apply the basic limit laws immediately yet. See what I mean? Okay, so we're gonna have to do some work around, right? So let's bring in some algebra. So in that way, the first step I'm doing, so now after proving that the denominator will have the limits going to 0, the first step I'm doing, I'm holding on to the limit work. Okay? But what I'm about to do now is that the square root expression, t squared plus 9 in the square root, and then minus 3. Okay? This is what I'm about to do. You guys happen to remember from algebra that we are allowed to do something like this? If you have a difference of 2 squares right here, you guys remember the factor product of this? What does it go into? If you have a difference of 2 squares, how do we factor that? A plus b times a minus b, right? Yes? A plus b times a minus b. And then it's just my case, I prefer writing a minus b times a plus b, but it's the same way. See what I'm saying now? But then we take advantage of this. We take advantage of that, and think about it. A lot of times you simply just have a difference, right? You can purposely, I'm saying that a lot of times starting with a difference or starting with a sum, you can purposely, so here I'm starting with a difference, you can purposely multiply with the a plus b over here. Now these two are called the conjugates, okay? The conjugate expressions. Or a conjugate pair. Yeah. These two are here. They're AB and AB, but that's one of them is a minus, and the other one is a plus. Okay? So the whole pair is called a conjugate pair. But if you're starting out with a minus, you can purposely multiply with the other conjugates, right, in the pair here. Or if you're starting out with an A plus B, then what's the conjugates for that? The conjugates for that is going to be A minus B. See what I'm saying now? Okay? But why am I doing this? Because sometimes we can, by doing this, we bring that back into the difference of two squares. Do you guys follow it? Okay? And so now, let me bring in for you a little hint here. The reason I talk about square is because square can indeed undo the square root, right? When you square an expression right here, you can cancel out the square root, right? You got the idea? Okay? And we have a massive square root right here. We have a massive square root right here. And that's why now, see, I'm trying to see this as, how about, let me erase the parentheses that I'm currently having here. It's a square root of whatever inside, right? So there's a square root term minus the 3, right? So we got a difference between some two terms. I want to get the square root away, so this is what I'm doing. And then, of course, over to t squared in the denominator. So I am going to purposely multiply to this expression here, it's conjugates. You guys following? So the conjugate is going to go like this. This is the square root of the whole t squared plus 9, but then plus 3. You guys following that like that? Okay. Of course, I mean, they taught, I'm pretty sure they taught you this thing back in your algebra days, but back in those days, it should have been a very deadly experience for any of us learning these, right? And we saw no point of learning these at that time. But now when it comes to calculus right here, that's where it pays off. Okay? And so, another rule of algebra to remind right here. Anytime you multiply an expression to the top, right, make sure to multiply the exact same expression to the denominator. So I just now multiply square root of t squared plus 9 and plus 3, right, to the numerator. We have to make sure to multiply that same expression to the t squared at the denominator as well. So we got t squared plus 9 in the square root plus 3, right? I multiply that to my denominator as well. Right? That's So now I can clear away all of these. All right, so what will this turn out for us? I still have not done anything with the limits, so I'll still keep that limit symbol hanging around. Okay. This is what I'm having with here. In the denominator, definitely it's just going to be t squared in parentheses or in product with the square root of t squared plus 9, right? Plus 3. See what I mean? Right. But see now, this is my famous conjugate pair right here, right? So difference plus, difference in sum, two exact terms repeated here. So it looks like I'm going to have this is square root of t squared plus 9, but I'm going to completely square that. And then I'm subtracting it because we produce a difference of two squares, right? I square the square root term and I'm going to square the 3 terms. Yeah, I'm going to square the 3 terms. You guys follow it? Right. So multiplying the two conjugates together, right? So now that's going to equal, well, I'm still leaving the limits. I still have not done anything with the limits yet, right? So the denominator stays the same still. Right? Square root of t squared plus 9 plus 3, right? But now in the numerator, this square now is going to cancel with that square root, right? Making it just perfectly t squared plus 9 with no more square root, right? We're subtracting the 3 squared, here is a 9. So now combining like terms, right? 9, subtract away 9. In my next step, I'm still just reducing down my algebraic expression right here. So I'm looking at t squared, right? The 9 is gone completely. So now I'm looking at t squared over t squared times the square root of t squared plus 9 plus 3. You see these algebra things back in your days learning it, and it was pretty deadly, but now you have reached a certain level of fluency, and it will come a lot easier. Right? So now, what's good about the t squared and over that common factor of t squared? We can cancel that t squared away, right? And now making your next move right here. It's still a limits problem that we haven't done anything on the limits yet. But it's reduced down to 1 over, right? And then now square root of t squared plus 9 plus 3. There you go. So now this is our safe zone point right here. This is the point that we have landed into our safe zone, right? Meaning basic laws or basic limit laws are ready for being applied here. Right? So yes, I'm short of space here, so a whole bunch of basic limit law steps right here. But at some point, right, you're going to reach into something like this. The limit of 1, right, all over, and then there's a square root, right, and then limit of t right here, all squared, plus 9, actually not on my, plus the limit of 9 here. Like I said, the dots here means I'm hiding a few steps right here, and I can kind of leave that for you guys. These are t going to 0, t going to 0, right? T going to 0. And I have one more term out here, plus the limit of 3 here as we're letting t get close to 0, right? Because I was so short of steps ago. So now when it comes to this point, we're just simply evaluating it. It's now going to be, that limit is a 1, right? So we get a 1 divided by, now I'm looking at the square root, right? And then 0 squared plus 9, and I'm adding 3, right? And then, so that's how we come to our final numerical answer. Like so it should be a, altogether the final answer is a 1, this little narrow space right here. It's going to come out 1, 6 altogether. That's our answer for that. There's 1 on top, right? And then in the square root at the denominator, we're looking at the 0 plus 9 is a 9, right? Taking the square root of 9 is 3 plus 3 after that, right? Call it now example 4. We still want to estimate, or I mean evaluate, right? It's going to do basically laws. This one pipe for x greater than 2. Right? Alright, so ready for work? So here's the thing. You see limits going that limit point unfortunately happens to be the breaking line of your piecewise function right here, right? Your piecewise got broken up into two separate pieces right around that line of x equals 2, right? And that's why taking the limit is a whole matter right here. But let me remind you one property. Remember, this limit law, right here, this, what we've learned even before limit laws, that the limit for a function when x generally comes to a limit point, that comes out finite, right? Only when the two-sided limits, one of them is coming to a from the left-hand side, right? The same with limits coming out from the function when x getting close to a from the right-hand side, only when the two-sided limits agree to the same value out. That's how you can make conclusion. And so our goal is to find that general limits, right? That limits where x generally coming close to 2 from both sides. Okay. But so we need to bring in this strategy right here because our function is broken up into two separate pieces. And it's different behavior on the left-hand side and on the right-hand side of our x equals 2 limit point again. So that's why we gotta bring in that fundamental understanding again. But of course, we don't want to use table values, right? I'm not attempting to use table values. So after reminding you that, let me erase it now. I need to bring in. I need to use a lot more space here. So from the left-hand side, but keep in mind no table values. The left-hand side, we're talking about if we're finding the limit of f of x when x gets close to 2, but from the left-hand side. You guys following that? Okay, so now I'm using this symbol. Okay. So finding the limits for this function when x gets close to 2 from the left-hand side, it means being on the left-hand side of 2. Being on the left-hand side of 2, which one of the pieces here indicating on the left-hand side of 2? Yes?
4 minus x.
Yes, the 4 minus x squared, right? See, because the condition is saying right here, anytime that you're looking at x less than or equal to 2, then your function has to be defined as this 4 minus x squared piece. You guys with me on that? Okay? So when you're taking the limits for x getting close to 2, we will not be at 2, right? But we're just going to be anywhere on the left of 2. So that's why it's completely legal to use this piece here. Are you guys with my explanation so far? So that means now I can, instead of writing abstractly the f of x here, we have the actual function to work with. 4 minus x squared. And we're taking the limits where x gets to 2 from the left-hand side. You guys see how it worked? See, so the sided limits here instructed us to use that proper piece that goes with it. All right? And so now basic limit laws comes in. So even though the basic limit law was written for, was intendedly written for just all of those general limits, but it also works on the sided limits as well. So now, even though you're only approaching 2 from the left-hand side, you can still do this. Limit of 4, right? Get close to 2 from the left-hand side, minus the limit of the x squared here to get close to 2 from the left-hand side. See, it's really the same basic limit laws that we've been applying, that we've been using, except for every limit point we put in the left side indication. Minus sign right there. So just like that, basic limit law says it has to come out being a constant 4. Right? This here, we can still apply that basic limit laws for the power, right, of a function. Now we can take the limit separately when x gets close to 2 from the left-hand side, right? We can square that, right? So for this simple function here, as x gets close to 2 from the left-hand side, see, don't think of that as negative, think of that as from the left-hand side. So in the end, it's still approaching 2, right? It's still getting close to 2. So now I'm talking about 4 minus 2 all squared, right? So now it's going to be 0 for that piece. We good with that then. So on the left-hand side limits, we found 0. Going okay with that? And then, but we still got the right-hand side. Right? So from the right-hand side, here's how I'm seeing it. The function there. Now if we're approaching 2 from the right-hand side, here's how I'm observing it. Just like how we decided earlier, now we're getting close to 2, but from the right-hand side, right? X values on the right-hand side of 2. So which one which one among the two pieces are we using here? You can just say it out loud. the x minus 1, right? The x minus 1, yes, there you go. The x minus 1 is the one that we apply. So we got the formula now, we got the actual function now. So now we just apply basic limit laws again. It allows me to do the following. X getting closer to from the right hand side, simply just on the x, right? And then I'm subtracting, see, term by term, I'm subtracting the limit of that constant term 1 here, as we let x get closer to on the right hand side. Right? So now that goes 2 minus 1, right? So from the right hand side, it comes out with a limit 1. See what I'm saying now? So the two-sided limits this time disagree, right? From the left hand side limit right here. So think about it. I mean, as a general conclusion, the limits of this function right here from the left hand side, okay, it came out to 0 as we found on the other board. But on the other hand, right, same function right here, you're finding it piecewise, the limits from the right hand side, okay, coming out 1. That's how I said earlier those two are inconsistent with each other, right? So now they don't agree, so that means the function here, this final evaluated limits coming generally to 2 from both sides, it comes out what? Does not exist. Okay? That's how it's done. Okay?